So this is our last lecture on thermal energy. We're going to talk about states of matter and changes of state. So the three main forms of matter are solid, liquid, and gas. There are others though. Plasma is one. It's a hot ionized gas consisting of approximately equal numbers of positively charged ions and negatively charged ions. Then we have other interesting things like super solids and super liquids, but we won't get into all of those in this course. That's far beyond the subject matter. You were very familiar with the changes of states of matter. Water, for example, can freeze to ice. It can melt from ice back to water. It can condense from steam to water, or water can be heated to become steam, so it can evaporate. And then you also have sublimation, when something moves from a solid to a gas directly. What we need to consider when we're changing states of matter is that there's also a kinetic energy to the particles, the molecules, in their different states. If you consider that the kinetic energy, which is the temperature, is based on the movement of the particles. Well, if something's a solid, the particles don't move as much, so it has less energy than if that material is a liquid, which moves more, which also has less energy than if the material is in its gas form, which is where it would move at its maximum amount of kinetic energy. So it would have a greater temperature when it's a gas. So write down this, the kinetic molecular theory. Matter is composed of particles that attract each other and have kinetic energy. The amount of kinetic energy that they have determines the state of the matter. So a solid, as I said this already, but a solid, the particles vibrate within the confines of the solid. The liquid form, the particles, they can move around, but they're contained by the size of their container. For gas, same idea. They're contained by the size of their container, but they also have more ability to move around. So more chance for interactions, more chance to provide, to transfer thermal energy. So as a substance absorbs thermal energy, it tends to go towards the gas state, and as energy is released, thermal energy is released, it moves towards the solid state. So changes of state, they may occur when a substance absorbs or releases thermal energy, and the thermal energy that is transformed into kinetic and potential energy. So let's look at how we move from one state to another. And there's actually, it's not just a straight linear equation. There's an amount of energy needed to change for something to change state. So this is a heating graph, and what this is showing is there are periods of linearity where we have the thermal energy being used to, or thermal energy being transferred in a linear equation where it just moves straight in a positive kind of sloped line. But there's also periods where we have changes of state occurring, ice melting, or water boiling. Those times, energy is being absorbed, but the temperature of the material is not increasing. Here's a cooling graph. Same idea. The temperature change is linear when we are within a state. When we're in the point where we're changing from one state to another, there is a period where there's energy being released, but the energy released is being used to change the state, so the temperature doesn't change. And those are periods where we have these horizontal lines. So you see the horizontal line at the condensation portion and the freezing portion. So when we look at these two graphs, one thing you might notice, this is for water specifically, the length of the line segment for water boiling and the length of the line segment for water condensing is equal. And the length of the line segment for ice melting and the line segment for water freezing is also equal. And this actually happens for all substances. And what this basically means is that amount of energy that's needed for the substance to change between water to air, or sorry, water to gas, and from water to solid. Sorry, I have to redo that. We're all talking about water. The amount of energy needed for something to change from liquid to gas, or from liquid, or from gas to liquid, is the same, and the amount of energy needed to change from liquid to solid and from solid to liquid is the same. But the amount of energy needed to go from solid to liquid is not the same as the amount of energy needed to go from liquid to gas. So there's different heat amounts that are required, different energy amounts that are required to change state, and they're the same whether you're going from when you're going from one state to a second state, or from that second state back to the other state. So let's look at, I've kind of talked about everything here on those graphs, but here's the here's a condensed version that you can copy down. So here they're asking us to just label this graph with the points where the material is a solid, a liquid, or a gas when it's melting or evaporating. I'll let you do that on your own. That's not that's something you can do for your own understanding. And here it's saying what is the melting point and the boiling point of the substance. So just reading from the graph, that flat line, the first horizontal line occurs at about 2 minutes. It is at about 55 degrees Celsius. The second horizontal line occurs at about 6 minutes, and it is 90 degrees Celsius. So that's where we see the melting and the boiling points of this substance. This is an example of a cooling graph. Any graph that has a negative slope would be a cooling graph for a temperature thermal energy graph. It says to describe each part of the graph. Well, there's those parts that have non-zero degree angles are changes in temperature, and the horizontal parts are changes in state. This question says, why does the temperature not change during melting, freezing, boiling, or condensation? So what's actually happening here is that the energy is needed to change the state. So when something is in a solid state, its bonds are kind of frozen together. The energy is needed to kind of break those bonds and sort of take them apart. And same thing as a liquid state. When there's bonds that are formed, there's a water is kind of in its liquid state, it sort of attracts other water molecules, and that bond has to be broken. So energy is needed to break that bond. To create those bonds, energy is needed as well. So that's what's happening during those changes of state. And this explains it in another way that you can read on your own in red. So now we're going to go into how to calculate things with this. So what do we call those horizontal periods of those heating and cooling graphs? Well, the amount of energy needed that's listed in that horizontal line segment is called the latent heat. it's the thermal energy that's either absorbed or released during a change of state. It's also given Q as a symbol, but sometimes we use subscripts to further define it. So let's look at another question here. This is a thought question. It says, to prevent fruit on trees from freezing and becoming inedible, fruit farmers in Ontario often spray their crops with water if they know the temperatures are going to drop below zero. So use your knowledge of latent heat to explain why this will help prevent the fruit from freezing. So it's not the frost itself or even the cold temperatures that cause damage to fruit trees. It's the formation of ice in the tissues of the leaves, twigs, and flowers and fruit that cause damage. So water keeps the tree and the fruit from freezing due to the fact that water releases heat when it freezes. In fact, each gram of water that freezes releases 80 calories of heat. It is this heat that raises the temperature of the tree, the air around the tree, and the soil, preventing ice formation in the tissues of the tree and the fruit. So that latent heat that we're talking about, that energy that's being used to break or form those bonds, there's also heat or thermal energy being released to the environment as well. So it's something you may not know about, but that's just an interesting kind of thing to think about. So we're going to define some terms. When something is changing from a liquid to a solid, so when something is freezing, or when something is changing from a solid to a liquid, when something is melting, we call that fusion. So Q with a subscript F is the latent heat of fusion. So we'll use that to define the solid to liquid transition. For the other transition, the liquid to gas transition, we call that vaporization. So that's the amount of energy released to change a liquid to a gas or from a gas to a liquid. And we call that Q with subscript V. So this, the latent heat of a substance is a quantity that is usually calculated and displayed on tables and charts like this. So we have the latent heat of fusion for different materials, the latent heat of vaporization for different materials, and the melting point and boiling point of those materials listed in this table. I think there's one in your book as well. So specific latent heat of fusion, LF, is the thermal energy required for 1 kilogram of a substance to melt or freeze. And the specific latent heat of vaporization, LV, is the thermal energy required for 1 kilogram of a substance to boil or condense. So that's how much energy you need per kilogram of material to have that change of state occur. So here's some definitions. The specific latent heat is L. And the specific latent heat of fusion is LF. Specific latent heat of vaporization is LV. So how do we use these algebraically? Well, QF is equal to M times LF, and QV is equal to M times LV. And that is defined later on this slide. So for latent heat, as well as finding out how our thermal energy changes, we also have to consider the amount of energy needed to change states. So we'd also have to do a little side calculation, or within our calculation consider the latent heat as well. So let's do a problem. How much thermal energy is released by 652 grams of molten lead when it changes into a solid? So the specific latent heats for lead are listed below. Let's we can just calculate this one here actually. it is QF because we're talking about fusion here. We're changing into a solid, so we're going past the liquid-solid barrier, so that's the fusion, or that's a situation where you have fusion occurring. So we have 652 grams, or 0.652 kilograms, times our LF, 2.5 times 10 to the power of 4. We have 16,300, or 1.6 times 10 to the 4 joules. That's how much energy is needed to change molten lead into a solid. So liquid lead to solid lead. That's how much energy we need to use. Another question: how much thermal energy is absorbed when a 350 gram bar of gold melts? So if we're talking about a melting gold bar, in this case we're talking about going past the liquid solid barrier again. So we're going to use the latent heat of fusion again. So that is 350, 0.35 times the latent heat of fusion, 1.1 times 10 to the power of 4. So we get 3,850, or 3.9. Did I do that correctly? It says times 10 to the 5. So 0.350 times 1.1 times 10 to the power of 4. Yeah, I think it's incorrect there. It should be 10 to the power of 3. 3.9 times 10 to the power of 3 joules.